In this lesson, we'll be talking about another of the arithmetic concepts that you'll need to master to execute problem-solving questions on the GMAT Focus Edition, and that's going to be the concept of division and factoring. So let's start by just breaking down the operation of division, probably more fully than you ever have before. So we've got some sample long division here of 5 dividing into 17. And the way that that works is we can determine that 5 will go into 17 three times, and we subtract out that 5 times 3, or 15, from 17, and we'd have a 2 left over. And so your result using remainder notation is 5 goes into 17 three times with a remainder of 2. And we call the 3 the quotient. So the quotient is the result of division as an operation. The 2, of course, is the remainder. It's the whole number left over from the 5 that didn't evenly go into 17. 5 itself is known as the divisor or factor, and 17 is what is known as the dividend. So our division notation for 17 divided by 5 can actually be written out a handful of ways. So first was obviously 3 remainder 2, as we see in the example on top of the screen. But we could also write this as an improper fraction of 17 divided by 5, and that's actually the most efficient path to manipulating any sort of mixed number or fraction with a whole attached is as an improper fraction or as just a fraction itself rather than as a mixed number. But as a mixed number, we could write this as 3 2/5. And we also could write it as a decimal, which is 3.4, which is 2/5 as a decimal, or 4 out of 10. So let's continue to just kind of break down how the remainder works. First, we know that there is a set range for remainders abstractly. We know that the least possible remainder for any division operation is going to be 0, and that's when the dividend is divisible by the divisor or factor. So, for instance, 15 divided by 5 would have a remainder of 0, and 15 is divisible by 5. Now, the remainder must also be less than the divisor, because if the remainder were to equal the divisor, you would actually have to add 1 to the quotient and reset the remainder to 0. So for instance, if you wanted to theoretically consider 5 dividing into 20 or adding 3 to that quotient of 3 remainder 2, you don't say 3 remainder 5. You actually increase the quotient to 4 because 5 goes into 20 4 times evenly with a remainder of 0. And your remainder over the divisor is equal to the decimal left over as a fraction. So that's how we got to 0.4 from the 2/5 in the mixed number. Now, there are some divisibility rules that, if you can memorize them, will help expedite your manual calculation throughout the exam. And really, we only need to go from 1 to 10. But first, we need to consider the idea of dividing by 0. And technically, for the GMAT focus, nothing is divisible by 0 because the result is infinity. And you can think about this theoretically. If I divided 17 by 0, 0 would go into 17 forever because it would never take away from the 17. But that is a non-real value because it doesn't have a defined finite amount. So technically, you're not going to be able to have an answer that divides something by 0 on the GMAT. Now, everything is divisible by 1 because the quotient is itself. 17 divided by 1 is 17. Dividing by 2 are the evens, and any integer with an even units digit is going to be even. So that's how you can test whether something is divisible by 2, just looking at whether the units digit is 0, 2, 4, 6, 8. And remember, 0, technically, an even. To test if something is divisible by 3, you can just sum the digits of the integer and determine if that sum is divisible by 3. So for instance, 96, the sum of the digits is 9 plus 6 equals 15, and 15 is divisible by 3, so therefore, so too will be 96. When you divide by 4, you basically just want to test if 2 divided evenly into that integer an even number of times. You're generally going to work through these divisibility rules on the GMAT in kind of a linear fashion to test for divisibility factors, prime factorization, those sorts of things. It's, falls back under that category of number properties. So you're probably going to be testing all of these to a degree, and it's really easy to just see if you could divide something by 2 and divide something by 2 again to get to an integer. Again, using 96, I can see that 96 divided by 2 would be 48. 48 also will be divisible by 2, so I can determine that 96 is divisible by 4 just by going, well, half of 96 isn't even, so I know it's going to divide in half again and produce another integer. 5 is probably the one people are most familiar with. If your units digit is 5 or 0, the entire integer is divisible by 5. Dividing by 6, you're just applying the concept of 6's prime factors of 2 and 3. So if you have an even where the sum of the digits is divisible by 3, that entire integer is divisible by 6. 7 is the one that's kind of a nuisance. There is out there a rule for 7, but it's probably more complex than just running the long division. We saw that long division doesn't take that long in past lessons. In this lesson, we can see it's not going to take that long. It's easier to just long divide when you encounter 7, but 7 isn't really tested for this reason all that much as an aspect of divisibility because there isn't a great shortcut. 8 is something is going to be divisible by 8 when 4 divides evenly into that integer. So it's basically the same rule as 2, just extrapolated to 4. So again, with 96, I knew that 4 went into 96, 24, which is an even number of times. Therefore, 8 will go in an even number of times as well. And sure enough, 8 goes into 96 12 times. Then 9 has an extrapolation of the same rule as 3, that the sum of the digits is divisible by 9. So for instance, 189, I know that is divisible by 9 because 1 plus 8, 9 plus 9, 18 is divisible by 9 as a sum. So 189 in its entirety is going to be divisible by 9. And lastly, divisible by 10 just means that the units digit is 0. And these are great logical estimation rules to know because they can expedite the final step of problems. If you know what the units digit or what the divisibility has to be, that can help you eliminate things and maybe avoid a final complex calculation on a problem solving question. So there are two ways that you're going to consider factors. The first is as an all factor pair chart, and your first factor pair is always going to be 1 and the integer itself. So we can see we're basically working through the factors of 72. So 1 goes into 72 2 times, and we're just going to go down the line with our divisibility rules. So 72, the 2 in the units digit is even, so we know that 2 goes into 72, and it does so exactly 36 times. Then we know that 3 goes in because 7 plus 2 is 9, and 9 is divisible by 3, and 3 goes into 72 24 times. Then we can actually proportionally find our number of times 4 goes into 72, because if you just take 1/2 of the factor pair chart and multiply it by a number, you then just have to divide the other half by the same number to figure out the continuous factor pairs. So because I multiply 2 by 2 to get to 4, I have to divide 36 by 2 to get to 18, and 4 goes into 72 18 times exactly. We know that 5 doesn't work because there's no 0 or 5 in the units digit, and then 6 has to divide in evenly into 72 because both 2 and 3 are factors of 72, and you can see as well the same resource of the multiplication and division offset would work with 3 to 6. That's a multiple of 2, take 3 times 2 to get to 6. And 24 divided by 2 gives us 12. So that allows us to manually recognize that 6 is going to go into 72 12 times based on the proportionality. We know that 7 goes into 70 evenly, and 2 is just 2 above that. So 7 won't go in evenly. But 4 went in an even number of times. So 8 must go in exactly half that number of times, or 9 times. And as soon as you go down on one side and start counting up on the other, you are done with your factor pair chart. So just some facts about factorization. The greatest factor is always equal to the least multiple, which is equal to the number itself. So 72 times 1 is 72. That's the least multiple. 72 divided by 1 is 72. That's the greatest factor. And of course, 72 is 72. And once a possible factor squared is greater than the dividend itself, you have identified all factors. So what does that mean? Well, in this case, we counted up all the way to 8, and those were factors in 72. But as soon as we get to 9, 9 squared, or 81, is actually greater than 72. So we know that each factor pair of 72 must include a value of 9, and this is a way for you to catch when you're done testing out your factor pairs with larger numbers, more complex numbers with bigger sets of factors on harder problem-solving questions. Your least common multiple is the first multiple common to two integers, and the greatest common factor is the largest factor common to two integers. So these are just some terms that you may be asked about in number property style questions in the quantitative section of the GMAT focus. So then the other way to factorize, which you may actually be more familiar with, is what is known as a prime factor tree. So we use the same number of 72, and we want to try to split it as evenly as possible amongst its factors to expedite the tree. So we could go with 8 and 9. And then we just continue to split that down until we reach its prime factors. So of course, 8 can be split into 4 and 2. 9 can be split into 3 and 3, and that's the end of the prime factorization of that branch, because you cannot split 3 into any other factors besides itself and 1. But then on the left-hand branch, we still could split out two 2's from the 4. The other 2 was already prime factorized. And now we could say that the prime number is going to be the integer greater than 0 with exactly two factors, 1 in itself. We know what a prime factor is. But every integer has a unique prime factorization. And in this case, with our example of 72, we know that its unique prime factorization is 2 cubed times 3 squared. And the only integer with exactly 3 factors of 2 multiplied by 2 factors of 3 is 72. If you remove any of those factors, you get a different divisor or factor of 72. If you add to those, you will get a multiple of 72. So we know that the 3 factors of 2 and 2 factors of 3, as soon as you have that, the integer is divisible by 2. And if you add to those factors of 2 and factors of 3, like say that you had 4 factors of 2 and 3 factors of 3, that must be a multiple of 72. And any combination of 3 2's or 2 3's as a product or fewer, because if there's just one 2, obviously 2 itself is a factor of 72, is going to be a factor of 72 as well. So basically, you're counting the prime factors to determine whether divisibility is or is not occurring. And always remember that 1 is not prime, and 2 is the first and only even prime number, because our true definition of prime is that it has that exactly two factors, 1 in itself, and 1 only has a single factor itself. So let's go over to the whiteboard and take a look at a couple of example problems to see how to execute on your Scratch work when you encounter these types of problems involving division and factoring on the GMAT focus. So as always, we'll want to set up our Scratch work A through E, put a little line over top, and skip to the end to figure out what we're being asked for. And we're being asked for what is a possible remainder. We have real numbers, so I'll probably write those out just in case there's an alternative tactic opportunity. And we got 2, 3, 8, 9, and 20. So we start taking notes from the beginning. We see if the result when integer x is divided by integer y. So that means there are no fractions, and I should always note that when it's a restriction. And we know that when we do x divided by y, the quotient or result is 36.45. And we want to note that we're being asked for a possible remainder. So this problem is seeking an inexact value or answer. And if that's the case, we have a logical evaluation clue. Because when you're being asked for what is possible as opposed to what is definite, you are potentially being tasked with deconstructing what's happening in the problem so that you can show a mastery of just how the numbers work. And that's what's happening here. So we might recall that our remainder over the divisor in any division operation is equal to the decimal leftover as a fraction. So that allows us to set up a proportion for the problem as set up. So we know that 0.45 can very easily be repurposed as a fraction as just 45 over 100. But then our remainder, which we can call r, over the divisor, which is y, has to be equal to that other fraction. And by dividing out the common factor of 5 over 5, we could see that r over y would be equal to 9 over 20. And we know that all remainders have to be integers. You can't have a non-integer remainder. So that means that r can equal 9. And if we go up to our answer choices, well, there's our answer. It's 9, and nothing less than 9 is going to work because any other equivalent proportion would require a non-integer to be involved. And we know both the divisor and the remainder have to be integers. So the least possible value of the remainder is 9, and it's the remainder that pops out when we do our little proportion in the at the beginning. So that's one thing you might see with divisibility involving remainders. But let's just talk about when there isn't necessarily a remainder, such as with this problem. So setting up our scratch work again, we got A, B, C, D, E, put a little line over top. And once more, we can see we're being asked for the least possible K. So that once more, with the least possible, is going to be a logical evaluation clue. So we have to read the problem to figure out what it's asking for first off. And we can see that the product of all the integers from 1 to k is divisible by 3150. Okay, so that basically means k with a little exclamation point, which is a factorial. And we'll talk about this in another lesson in a little bit more detail. But factorial just means k times k minus 1 times k minus 2 all the way down to 1. And we're looking for the least possible value of k. So we need to break down the factors of 3150 because we know that basically that k factorial has to be divisible by 3150. As we talked about, you always want to start by pulling out the clearly most obvious and somewhat equivalent factor of the product that you've got, the dividend, as it were, here. So I can see clearly that 50 has to divide in evenly because anything that ends in 50 is going to be divisible by 50. It's just the way the numbers work. And if I did 50 goes into 3150, little long division, it seems like it's going to take a long time, but it doesn't because 50 goes into 315. We know that's 6 times. We then subtract out 300 because 50 times 6 is 300. And then we drop down the 150, and 50 goes into 150 3 times evenly. So 63 is going to be the other half of this prime factorization tree. Then we've got to break out our 50, which of course is 10 and 5. The 5 is done, and then we've got a 5 and a 2. Then for the 63, you might recognize 7 and 9. And then from the 9, we've got 2 3s. So I know the prime factorization of 3150 is equal to 1 2 times 3 squared, or 2 3s, times 2 5s, or 5 squared, times 7. So I know that k factorial must include 2 5s, 2 3s, 1 2, and 2 7s. Or sorry, not 2 7s, 1 7. So now I've just got to go through my possible answers, which I could have started out by writing here. We got 5, 7, 9, 10, and 15. So because I'm being asked for the least possible K, I'll start at the top. Well, if I look at 5, well, 5 has no 7s. So that's out immediately. Now, 7 is not going to have a 9 or 2 3s. Well, actually, it will have 2 3s. It'll have 2 3s from 6 and 3, but it won't have a pair of 5s because you only get the one 5 at 5, but there's no second 5. So that's going to eliminate 7. With 9, we still have no second 5. But with 10, we get two 5s from 10 and 5 itself, along with 1 7 at 7 in the factorial, 1 2 that you get from the beginning to, and of course a 9 as well. So you can see that it's the deconstruction of the number that you need to execute on this type of problem where they're asking about divisibility. So go ahead and practice some factor and divisibility problems on your own to improve at this somewhat more complex concept of our honestly entire arithmetic system to improve on the quantitative section of the GMAT focus.